This is section 2.6, rational functions. We just came off of higher degree polynomials where we were looking at end behaviors, x-intercepts, and we were using those to graph those. Now what I must warn you about is there is going to be kind of a shift because rational functions are kind of a whole nother monster. So the idea is we're still warming up to write our chapter books. The first chapter is going to be about quadratics, the second about higher degree polynomials, and then the third is going to be this one, rational functions. So to do this, what we're going to need to do is identify key features of rational functions. I'm going to be providing a step-by-step approach to identifying these key features, and then what we're going to be doing is using those key features to graph these rational functions. So the first thing that I would like you to do is this activity where you're going to make predictions about what this graph looks like. So make some observations and then make some predictions about what it looks like. If you're not really sure what it looks like, then you're going to be left to do an XY table and then graph it. Okay, so put me on pause because I'm about to expose the answer. There it is. So what I would have you notice is that maybe in your predictions you said, hey, I know anything divided by itself would reduce down to just 1, right? Because we could reduce or simplify these and we would get 1. So note some of these x values. If you were to plug those in, plug -2 in for x, you would get -4 on top and -4 on bottom as well, hence the 1. But the one thing that I would like you to observe is this one right here. If you were to plug 2 in for the x, what would happen is an error in your calculator because you would have 0 divided by 0, which dividing anything by 0 we cannot do. So you can't see it on this graph that I graphed because, hey, once again, it looks just like y equals 1. But because of the original function, if you were to zoom in on this graph at x equals 2, we would actually have a missing pixel. And we'll play with our graphing calculators with that and see that yes, we are going to have a small little hole in our graph. Activity 2, I want you to make predictions about this graph, make some observations, try to figure out what's going on with this. I'm going to expose the answer, so make your graph. And here's what this one would look like. So again, we have this error, and it's again occurring where we could simplify, right? We might as well have just graphed y equals x minus 2, where -2 is the y-intercept, and we have a slope of 1, so rise 1, run 1, rise 1, run 1. But the idea here is, once again, you have that error because if you had plugged in -3, like this factor would have been fine, but this one is going to be 0 over 0 again. So 0 divided by 0 would have caused that error. So if you look at -3, we could do this on our graphing calculators, zoom in very close around the x value -3, we would have a missing part because that's not possible. Finally, make a prediction about this graph right here. Alright, and again, you're probably seeing that. Go ahead and graph it, make your XY table, and what you'll notice is that, hey, we might as well have just graphed x squared plus 4x plus 3, but we have that error because of that factor that's on the top and bottom. So, what are some assumptions or conclusions you have about graphing rational functions? Right now I would like you to jot down 2 predictions or 2 things you know about rational functions. So go ahead and do that in this portion of your notes. But if you have no idea what rational functions are, you still had to make some observations. But here is what a rational function is. Rational functions are functions that are expressed as quotients of polynomials. So in case you had no idea what rational functions are, you jotted down some observations, but this is that definition that you may have been looking for. So all we're doing is we're dividing 2 polynomials. And you would notice down here we have a polynomial x squared minus 4x minus 5 over, and then x squared minus 4 are divided by. So here are a rational function, or here's an example of rational function. We'll be using this one all the way through our slideshow, so we'll eventually be graphing this thing. The key elements, like I said, that you're going to have to be watching out for are x-intercepts and y-intercepts, holes, vertical asymptotes, and then also domain. That's going to go right along with the holes and the vertical asymptotes, and then horizontal asymptotes. So I'm going to be giving you a step-by-step method of finding these particular key elements. So step one, we're going to get the rational functions in factored form. So this is going to be one of the ones that we're going to be looking at, and this is the other one, and we're just going to carry this all the way through and eventually graph these both. So for this first one, this 3x minus 6, what I want you to acknowledge is that on the top, we could factor this because there is a common factor in each one of these terms separated by the subtraction sign. There's a 3 that we could divide by both of these, and then so therefore we can't just divide everything by 3 without saying, hey, I have changed it, so let's multiply by 3 to say, no, we haven't changed it. I've divided by 3 and multiplied by 3. But when I reduce these, I'm going to 3 on the outside, and then 3x divided by 3 is x, minus 6 divided by 3 is 2. And you'll note, though, we'll get that same thing, 3x minus 6. All over x minus 2. B, if I were to factor this, again, I'm looking for two numbers that multiply to be negative 5 and add to be negative 4. So maybe you're seeing this, but I'm going to take negative 5 and then positive 1, and those would be two numbers that meet that requirement. Down here, that's one of those perfect squares minus a perfect square. So hopefully you're recognizing that as that conjugate where we have exactly the same factor except for opposite second parts. Step 2 is find what we call wholes. Wholes occur where there is a common factor on the numerator and denominator, and maybe in your activities you noticed that that's what was happening here. So what we're going to do is we'll reduce the function by simplifying it, but recognize a whole by sending those common factors that we were kind of reducing out of there, but we're going to set those factors equal to 0 and solve for the x to find where that error would occur. That whole is going to occur there. So we're going to use the simplified function to find the y value. So here, when we did factor this, we got that 3x, the 3 times x minus 2, but there was a common factor, right? So what we're going to do is simplify down this to 3. But I'm going to set that x minus 2 equal to 0 because that's where there's going to be a problem. X minus 2 equals 0, so at x equals 2 there is a whole. So at this point though, it's a little bit tricky, but what you're going to want to do is you're going to want to plug in 2 to your function, and this one's kind of funny because it's always going to be 3, so plug in 2, you're going to get 3. 2 comma 3 is where our whole will be, right? Because this function 3x minus 6 over x minus 2, like we said, we might as well have just graphed 3, so why not use this 3 to figure out what was that y value of that whole? Alright, so here, this is actually not one, this is kind of a fresh one. Let's say we had this factored form. So let's say we were trying to graph this function. What I would like you to acknowledge is that we have this x plus 2 and then x plus 2 that we could cancel out. So we might as well have just graphed this function, but we have to acknowledge that at x plus 2 equals 0 there would have been a problem, so x minus 2 is where there's going to be a whole. Plug in negative 2 into this simplified function, so that's where I did that right there, and we're going to get negative 1. Because remember, this function is technically the exact same as this function except for one little pixel. This graph, if you plug that into your calculator, will get an error that negative 2. This one will not. Alright, so here is where our whole is. Here's that other graph that we're going to follow through all this. This one doesn't actually have a whole because when we factored it, there was no common factors on top and bottom, so this one has no whole. And that of course could happen. So now what you can do is you can use that reduced form to determine the rest of the key features. You've gotten rid of this whole in the calculations. We need to reduce our original rational function, and then we'll just be working with that simplified form and recognize that there was that little hole there. So wholes, that was the first step. Step 3 is going to be find your x-intercepts. Remember, x-intercepts are the x values such that this function equals 0, or that the function y equals 0. So in other words, the x values that make the numerator equal to 0. Alright, so this is big. So what we're going to do is we're going to set that numerator, or the top, equal to 0 and solve for x to find our x-intercepts. So sorry, I kind of switched around those two examples. I'm going to start with the b one. So here again was the original function. This is it when we factored it. So what we just need to do is set x minus 5 equal to 0 and this x plus 1 equal to 0. and I didn't really need the parentheses there. So when we add 5 to both sides, we're going to get x equals 5, and this one subtract 1 from both sides, x equals -1. These are the x values of our x-intercepts, or the x values that will make this function equal 0. Alright, this one, 3 is the numerator, right? Because we're over 1. So this will never equal 0 on the top, so there are no x-intercepts for this particular one. Alright, the next step is vertical asymptotes. So we found holes, we found the x-intercepts. Now we're going to have to find the vertical asymptotes. But what you're going to have to know is, what is a vertical asymptote? Well, in a rational function, this is a line, a vertical line, I should say, that your graph will approach infinitely, but never ever touch. Okay, so vertical asymptotes will never be touched. It's also a value in the graph that will be undefined and therefore is not part of the domain. So keep that in mind. You cannot plug an x value in it, so that's why we have no part of the graph that touches it. Alright, your answer should look in this type of form, x equals like 3, for example, because that's the form of a vertical line. Alright, so also a definition, this is on your book on page 166. The definition of a vertical asymptote is where your function increases infinitely or decreases infinitely as x approaches it from the left or right. And we're going to approach it infinitely but never cross it. So step 4 is going to bring us to finding those vertical asymptotes. What we're going to do is we're going to set that denominator equal to 0, because those are the values that are going to cause an error in our function, and we can't have that. We can't plug in those values on the bottom that's going to make it 0. So we're going to set x minus 2, x plus 2 equal to 0. When you solve for each one of those, what you're going to get is x equals 2, x equals -2. So therefore this is a vertical asymptote. This is a vertical line that is also a vertical asymptote. We are going to draw dotted lines on our graph to represent these lines that we cannot cross, dotted lines. Alright, example number 2, that other one that we've been following along, is that function f of x equals 3. This has no vertical asymptotes because, again, our denominator is 1 and it could never be 0. We won't have any errors. So do not let asymptotes versus zeros confuse you. Zeros, or the x-intercepts, are when we set the top equal to 0. Vertical asymptotes are the ones that cause us problems. They're going to be when the bottom equals 0. Step 5, we're going to find the y-intercepts. So y-intercepts are the place where it crosses, the y-axis. And what those values, we might not know the y value of the y-intercept, but we do know that x values are always 0. So we're going to set the x value equal to 0. Step 5, set x equal to 0 and find the y. You can do this into the original function, or the factored form is fine. I kind of switched back to the original. But just use the factored, it's fine. But either way, you're going to get 5/4 when you plug in 0 for your x's. So this thing's in the way, sorry. 0, 5/4, or 0, 1.25. Alright, and then this other one that we've been following, you can go ahead and plug in 0 for x, but no matter what, this function is always equal to 3. So 0, 3 is our y-intercept. Finally, step 6, this is kind of the new one. Horizontal asymptotes. These are end behaviors. Remember, with the higher degree polynomials, we would look for the end behaviors, and we would look at the leading term to determine that as x approaches infinity, what's y doing? Alright, well, we're still going to have these end behaviors, but sometimes instead of as x approaches infinity and then y approaches infinity, we might have y approaches some sort of horizontal asymptote. So it could approach 1 and never cross it. So long division is necessary, or I actually have a shortcut. We could use the long division, divide these rational functions, which are division problems technically, and whatever you get as the quotient without the remainder, that's going to be the quotient without your remainder, that's going to be an indication of what your end behaviors are. But what we're going to do instead is we're going to use this shortcut. It's Bobo, Botan, eats DC. Bobo stands for big on bottom, y is 0. Botan is big on top. Big on top, there is going to be none. Okay, e to c is exponents are the same, divide coefficients. Sorry, this thing won't disappear. So this right here, what Bobo-Botten eats DC, it's a study of the degree of the polynomial on top and bottom of the original rational function. So all of these steps after the factoring process and the simplifying, we just use the simplified version. This one we should go back to the original function, the original one that we started with. So we're going to study the degree of the polynomial on top and the degree of the polynomial on bottom. So here again is just the breakdown of what Bobo-Botten eats DC is. Alright, so here again is that one of our functions that we've been following. Alright, so technically this one's a little strange, but we have x to the 0, x to the 0, so the degree on top is 0, and the degree on bottom is 0. So this is going to be the case of eats DC, exponents are the same, so divide coefficients. So our end behaviors are actually going to approach as x approaches infinity, y approaches 3. And as x approaches negative infinity, when we divide these coefficients, 3 divided by 1, y approaches 3 as well. Alright, so same thing here. Sorry, I didn't give you a very good variety here. But this is a degree 2 polynomial and a degree 2 polynomial. So once again, we would have exponents are the same. So these would be the same end behaviors except for, actually not really, as x approaches infinity, y approaches 1, and as x approaches negative infinity, y approaches 1, because again when we divide our coefficients we would have gotten that our end behaviors approached 1, and this is our horizontal asymptote. So horizontal asymptotes though, you can draw another dotted line, and just like we have a special form for vertical asymptotes, for horizontal asymptotes, this is really y equals 1 would be the dotted line we draw, and this one y equals 3 is the dotted line we draw. Okay. Alright, so there were all of our steps, and now what we must do is graph using our key points. Alright, so this one's kind of a simple one because we do know what this graph looks like. It looks like y equals 3. But find the holes. We found the hole. It's 2, 3, so over 2, up 3, there's a hole. I am going by ones. Okay, so we'll draw that. It's kind of like a point, but we're going to do it empty. There are no x-intercepts. There is no vertical asymptote. There is a y-intercept at excuse me, at 3, 0, 3, and then find the horizontal asymptote. Well, that you could do like a dotted line, and what our end behaviors are always and constantly going towards is that line. Alright, but in this case it's not really a horizontal asymptote because we are just, that's what we're approaching always, I guess. So our end behaviors are always approaching it, and they actually achieve it in this particular situation because it's a little bit of an odd situation. Normally our end behaviors approach it, but they do not cross it. Alright, this one, I've gone ahead, if you want to step through all of our PowerPoint slides about it, but what we did was we found holes, and there were none because there were no common factors. We found the x-intercepts, or our roots were 5 and -1, and again the x-intercepts, we set the top equal to 0 because we were trying to figure out where is this function equal to 0, and what we found was 5, 0, -1, 0, so I got those down. Alright, find the vertical asymptote. We found 2 because we could set both of our factors on the bottom equal to 0, so there are our asymptotes, our vertical asymptotes, and you can see those with the dotted line. Find the y-intercepts, right, a little bit above 1, 0, 1.25. Find the horizontal asymptote. That we did with Bobo-Botten eats DC. Right, we found that the horizontal asymptote was y equals 1, so we know our end behaviors are going to approach those. So now graph all these key points. Now, with a more trained eye, and as you guys experience these, what you can start to do is do your end behaviors. Okay, so this one's my last point known, so I can go ahead and jot that I'm approaching that end behavior, that y equals 1, but never crossing it. Okay, as x goes towards infinity, y is getting closer and closer to 1. Over here, there's a couple of ways we can do this. You could either draw a line like this, okay, and let that end behavior approach it, but we do not have any x-intercepts. So we could not do what I just did because there would have to be some sort of x-intercept. All right, so we're going to have to draw something up here and approach that end behavior but never cross it. Now, asymptotes, by definition, are as we approach them from the left or right, they have to shoot up or they have to shoot down. I'm going to have to go up for this one because, again, if I shot down, I would have an x-intercept, which I do not have. These are the only places where our function is going to be equal to 0 with those factors or those x-intercepts. So I can't just create a new one. Alright, so here I'm going to connect the dots, alright, and again you could try to shoot down, but you would create another x-intercept, so I have to shoot up as I approach that asymptote. Same thing here. There is no bouncer or anything, so I'm not just going to bounce up. That is a possibility, but I'm going to have to go down. Cross through that x-intercept, go straight through, and go down. Alright, this one, again, there is no bouncer, so I can't kind of bounce up. I'm going to have to go straight through. I knew my asymptotes, okay? So, or my end behavior, and then this I have to approach infinitely in the negative direction. Alright, so if that was just beyond you, these key points I used, and then I kind of made some sense of where they had to go. But if you are in any doubt, what you should do is an XY table. You had those key points, plug in something like -3. And if you plug in -3, just plug it into either one of these functions. But we were going to get -8 and then times -2 all over -5 and then times -1. Okay, so what we have here is 16 over 5. And if you went ahead and did that division, you're going to get like 3/1/5. So -3, go back 1, 2, 3, and go up 1, 2, 3, and 1/5. So right about where I had it. But as you plot in more points, that's fine to do. Get as many as you need so that you can start to see the visual of what this function's doing. All right, so your homework is a worksheet. We'll work on that together.